All right, so I'm a huge fan of looking through problems and seeing what they're ultimately asking us to solve for. And if we go to the very end here, they're going to say to us here, calculate the equilibrium constant Kc. And they actually ask you to round the answer to significant figures. So if they're going to ask us to solve for the Kc, we need to know what the equilibrium expression is. Now, equilibrium expression also goes by other terms like the law of mass action, but we have this equation right here, and we're going to have to write a Kc for it. So I'm going to do this right away, and I'm going to acknowledge a couple things that are true. Thing number one that's true is that gases and aqueous are able to be put into our equations. Other than that, solids and liquids are not. So even though they give us this equation and they give us the information about it, we're not going to use that at all for our equilibrium expression. So this is going to be canceled out, as is this solid over here. So the only two things we're looking at are these two, which makes this a lot less tedious when we're looking at it. We'll come back and we'll look at the 9.4 liters and the grams of each thing when we're actually solving. But the first thing we need to do is write our equilibrium expression. So over here, I'm going to write Kc because we're dealing with concentration. Now, I'm going to take a brief timeout here, commercial break, to say this. See how this is in gas? These are both gases. So whenever you have an equation that's written in gases, you have two options. You can either do Kc or you can do Kp. You'll do Kp when they give you pressures. In this particular problem, they've given us grams and they've given us liters. We should know this. These grams are going to lead us to moles. And if we have moles and we have liters, we can figure out the molarity, which we're going to plug back into our equation. So time back in, we're going to come back to our equation, and now we're going to do the concentration. So what do we have over here on this side? We have H2O, but we also have the coefficient of 3. So we're going to do this. We're going to put the concentration of H2O all raised to the third power. All of that over, and on this side we have our only gas, H2, and it has a coefficient of 3. So we're going to put it over here. We're going to write H2 concentration, and it's going to be also cubed. Now that we've gotten that out of the way, we need to be able to find what the actual concentrations are here and here. And if we have that, we can solve for Kc. Now, if they've been gentle, they could have actually given us the concentrations in this particular chart, but they didn't. So they're going to leave it to us to figure out the concentrations of the only two things that matter. And I'm going to do this right now because I don't want to have us potentially having an issue with this and working with it. I'm going to put a line right through this, a terrible line, and I'm going to put a line right through this one right here. So both these right here, I'm going to put a bunch of lines because I'm very angry about it. So these two right here, I'm not even going to worry about the rest of the problem. So that means that all I have to worry about is converting H2 concentration. Oh, that's a delightful gray color. The H2 concentration to molarity and the H2O concentration to molarity. So let's start off with our H2 concentration. And we're going to have to do our basic train tracks, which I don't like that color. Let's go back to our very soothing blue color. I'm going to start off with my 3.66 grams of H2. And I'm going to put into my little table here and divide it by its molar mass. Now, if you've done this millions of times, but the molar mass of this is 2.16 grams of H2 for every 1 mole of H2. And when I do the math on that, I get 1.816 moles. So I know that's my moles of H2. I need this because they've told me that the volume is 9.4. And I probably should have done this before, but here's where we're going. We want to figure what the molarity is, and molarity is always moles divided by volume. So if we can figure out the moles right here, and we know what the volume is right here, we can then get our molarity and plug our molarities back into our equation. So that's the plan here. So we have the 3.6, and now we're going to go over to our H2O. And our H2O starts us off with 2.42. And again, these are numbers you probably are fairly familiar with. It depends on your periodic table how in depth you want to go. I'm going to go 18.02 grams of H2O for every 1 mole of H2O. And when I do the math on this one, I don't know why it looks like I have an extra decimal in there. I'm going to change that, 1.886. And over here, we're going to end up with 0.134, and I'm not going to go any deeper because I only had 3 significant figures here, but 0.134 moles of H2O. Now, we're going to take both of these values and we're going to plug them back in to this equation using 9.4 as our volume. When we do that, for both these, we're going to get both our H3O concentration and our H2O concentration. Now, just to make this fun so we can keep this around, I'm going to drag this down here so we can work off of it. And again, let's take a look at what they've given us. We now have for our molarity for our H2, and I'm going to just write H2 down here. You do not need to do that. We're going to go 1.86 moles of our H2 all over our 9.4 liters. And when I do that, I'm going to end up with a molarity of 0.1932 molar. Now, here's the thing. Along the way in the problem, you can keep as many significant figures as you want. But the reality is, as soon as they gave us this 9.4 liters, they've told us the answer can only have 2 significant figures. Again, they in these problems often tell us specifically they want 2 significant figures, right? If they hadn't, we could go back on this and go, wait, there's 2 significant figures here. Now, the sooner you round, the more farther off your answer can be. So I'm going to keep these significant figures and I'm going to cut them all off at the very end. So we've just done our molarity for our H2. Now let's do our molarity for our H2O. And in this case, it's going to be the 0.134 that we got up here. We're going to put that down into here and go 0.134 moles divided again by the same 9.4 liters that they gave us in the problem up here. And when we do the math on this, we're going to end up with 0.01429 molar. Now, we are delighted by this because now that we have these variables right here, we're going to grab this guy again and bring them down here. Now that we have this, can't we plug these numbers right here into the spots where they belong? So this right here, this is my molarity of my H2. Wouldn't I put that down here? And this is my molarity of my H2O. Wouldn't I put that right here? So I'm going to do it right beside it, and I'm going to write in here our 0.01429, and all that's going to be cubed all over 0.1932. And again, I'm leaving out the units here because whenever we're solving for our Ks, we don't have to put our units in. And when we do that, it's going to equal 4.0 times 10 to the negative 4. This right here is our final answer. And if you note here, we've used the 2 significant figures they're asking for. So our Kc has been solved. Hopefully this has been helpful.